All right, let's dive into one of the biggest headaches in training a really powerful class of generative models. These things called undirected probabilistic models, like restricted Boltzmann machines. Now, these models are fantastic, super expressive, but they've got this computational monster hiding at their core that makes learning from data seem, well, almost impossible. So how do we actually do it? That's the puzzle we're going to piece together today.
So here's our game plan. First, we're going to meet the villain of our story, this thing called the intractable partition function. Then we'll see how the math of the learning process itself gives us a clue, splitting the problem into two distinct phases. This leads us right to the hero of the day, a really clever trick called contrastive divergence. We'll break down exactly how that algorithm works, and then we'll wrap up by looking at some of the practical ways it's been refined and used in the real world.
Okay. First things first. Before we can even talk about the solution, we have to have a deep respect for the problem. And really, the entire challenge of training these models, it all boils down to one single value that is just a computational nightmare to calculate. And this is it, the partition function, pretty much always just called z. Now, on paper, its job looks totally straightforward. You see, energy-based models give a sort of score, an unnormalized probability, to every possible input. Z is just the grand total of all of those scores, summed up over every single configuration the input could possibly take. You divide by Z, and boom, all your probabilities now add up to 1, just like they should. It's the denominator that makes the math work. But here's the punchline. While Z looks innocent enough in an equation, actually calculating it is, well, it's a disaster. For any data that's actually interesting, like images or text, a direct calculation isn't just slow, it's fundamentally impossible. It's just not going to happen with any computer we have or can even imagine. And this slide really breaks down why. The number of possible inputs just explodes exponentially. Let's take a tiny 28 by 28 pixel black and white image. That's 2 to the power of 784 possible images you can make. That number it's just ridiculously huge. It's way, way bigger than the number of atoms in the known universe. You literally can't sum them all up. And here's the real problem. If you don't have Z, you can't get the true probability of your data. And if you can't do that, you can't calculate the gradient you need to train your model. We're completely stuck. Or are we? So let's see what happens if we look a little closer. Even if we can't calculate Z, we can still look at the structure of the gradient. And it turns out the equation has this beautiful symmetrical form that gives us a way to approximate it. It's like finding a tiny crack in this giant computational wall. So, amazingly, the gradient we need splits into two parts that are pushing against each other. First, you have the positive phase. This is driven by the real data you're showing the model. Its job is to say, hey, this stuff is real, increase its probability. Then you have the negative phase, which does the exact opposite. This part is driven by samples the model generates itself. You can think of them as its dreams. And its job is to say, okay, now lower the probability of these things you're just making up. And this is really the core intuition. The model is learning through a balancing act. The positive phase keeps it grounded in reality, but the negative phase is absolutely crucial. Without it, the model could just learn to assign a high probability to everything, which would make it totally useless. It has to learn to tell the difference between what's real and what's not by contrasting reality with its own little fantasies. Okay, but hold on a second. This leads us right into a really annoying paradox. That negative phase needs samples drawn from the model's own distribution. And to get a good sample, you usually need something like Gibbs sampling, and you have to let it run until it settles, which is super slow, and the whole thing still kind of depends on that Z we were trying to get away from in the first place. It feels like a total catch-22. This is where the magic happens. This is where Geoffrey Hinton's really clever idea, contrastive divergence, or just CD, comes into play. It's a pragmatic, powerful shortcut that just smashes right through this vicious cycle. And here is the core insight. Forget about starting a markup chain from some random noise and waiting around forever for it to converge. Instead, we take a real data point, one from our actual training set, and we start the chain right there. Then we only let it run for a tiny number of steps, sometimes just one single step. So why on earth does this work? Well, the sample you get after just a few steps is definitely not a perfect, independent sample from the model's true distribution. But it doesn't have to be. What it is a sample that's moved just a little bit away from reality towards a place the model currently thinks is more plausible. It's like a reconstruction that's still tied to the original data. And that provides just enough contrast to form a useful negative gradient. It's a beautiful approximation. So let's get into the nitty-gritty of how this actually plays out. We can break the algorithm, which is called CDK, where K is just the number of Gibbs steps, into a really clear blueprint.
So here's how it goes. First, you just grab a small batch of your real data. Second, you calculate that positive phase gradient. You're telling the model to like this data more. Third, you take those same data points and use them to kick off your short Gibbs sampling chains. The samples you get out are your negative or fantasy samples. Finally, you calculate the negative gradient from those fantasy samples, and you update your model by nudging its parameters in the direction of the positive gradient minus the negative one. It's simple, it's elegant, and it just works.
Now, CDK is really the foundational algorithm here, but of course, in the real world, researchers have come up with some pretty important tweaks and refinements to make it work even better.
Probably the biggest refinement is something called Stochastic Maximum Likelihood, or SML. You'll also hear it called Persistent Contrastive Divergence. The idea is simple, but really powerful. Instead of starting the Gibbs chains from scratch with new data every single time, we just let them keep running. We have this persistent set of chains, and between each update to the model, we just run a few more Gibbs steps on them. This lets the chains explore the model's dream space a lot more thoroughly over time, and that can lead to a much better approximation of that negative gradient.
But of course, there are trade-offs. SML can definitely give you better models, but it's also a lot more delicate. You have to make sure that those persistent chains are mixing, moving around the space, fast enough to keep up with how the model is changing. If your learning rate is too high, the model can shift dramatically, and the chains get left behind, stuck in an old part of the distribution. This is a classic way these models fail. You're training on MNIST digits, and suddenly, your model will only generate the number 7, over and over, because it can't escape that one mode. It's something you really have to watch out for.
And all of this leaves us with a really fascinating question. Contrastive divergence was a brilliant hack, right? It made this whole class of models trainable when they otherwise wouldn't have been. But is it just a necessary compromise we have to live with? Or does this whole struggle really point to a more fundamental weakness in energy-based modeling? In fact, you could say this exact difficulty is what fueled the search for completely different approaches, leading to the rise of things like generative adversarial networks and VAEs, which were explicitly designed to sidestep this whole partition function problem. It's a key question that's still driving a ton of research in this space today.